What if the universe had an edge? Not a metaphor, not the limit of what we can see, but a real, physical boundary. A place where space itself simply ends. Imagine traveling in one direction for billions of years, past galaxies, past clusters, past the faint afterglow of the Big Bang. The cosmic web thins. Matter grows sparse. The darkness deepens. And then ahead of you something appears, a boundary, a surface, a final wall in reality. What would that even mean? To understand this, we first need to separate two very different ideas: the observable universe and the entire universe. The observable universe is the region light has had time to reach us from since the Big Bang, about 13.8 billion years of cosmic expansion. That sphere stretches roughly 46 billion light years in every direction, because space itself has expanded while light was traveling. But that horizon is not an edge, it's a limit of visibility. The real question is deeper. Could space itself have a boundary? When we imagine an edge, we instinctively picture something like the edge of Earth, a cliff dropping into empty space. But that intuition comes from living on a planet embedded in a larger environment. The universe, by definition, is the totality of space and time. If it had an edge, what would lie beyond it? Another universe? Nothing. And what does nothing even mean in physics? Let's start with geometry. Modern cosmology tells us that on large scales, the universe is remarkably uniform. Measurements of the cosmic microwave background, the faint radiation left over from the Big Bang, show that space is extremely close to flat. Not curved like a sphere. Not curved like a saddle. Flat to within a fraction of a percent. In a flat universe, space can extend infinitely in all directions. There is no boundary, no center, no edge. But flatness does not necessarily mean infinite. A surface can be flat and still finite if it wraps around itself. Picture a video game world where walking off one side of the map brings you back from the other. In mathematics, this is called a toroidal topology. From inside, it feels endless. Yet its total size is finite. There is no wall, no boundary, just continuity. So already, we see something subtle. Having a finite universe does not require having an edge. But let's push further. Suppose the universe did have a true boundary, a physical limit where space-time terminates. What would happen as you approached it? According to Einstein's general relativity, space and time are not a static stage. They are dynamic, flexible, shaped by energy and matter. If space-time simply stopped, the equations of general relativity would break down at that boundary. You would have a discontinuity in the fabric of reality itself. Physics does not like discontinuities. In every tested model, boundaries require conditions. Surfaces have properties. Even black holes, regions from which not even light can escape, do not represent edges of the universe. Their event horizons are boundaries in space-time geometry, but space-time continues inside them. The singularity predicted at their center is not a wall in space. It is a breakdown in our understanding. An edge of the universe would represent something even more radical, a place where space has no extension beyond. Now imagine you are traveling toward this edge at near light speed. Galaxies behind you fade. The cosmic background radiation cools. Ahead, perhaps you see a shimmering plane. As you approach, what would occur? One possibility is reflection. If the edge behaves like a mirror, matter and radiation might bounce back. That would create observable anisotropies, preferred directions, in the cosmic microwave background. We do not see such patterns. Another possibility is absorption. Particles reaching the boundary could vanish. But this would violate conservation laws unless the boundary itself carries energy and momentum. And then there's the deeper problem: coordinates. In physics, position is defined relative to space itself. If you ask, where's the edge located? You're assuming a larger embedding space in which the universe sits. But our best models describe the universe as self-contained. There is no higher dimensional arena we have confirmed experimentally. Some speculative theories, like certain models in string theory or brain cosmology, propose that our universe could be a three-dimensional membrane embedded in higher dimensional space. In such frameworks, what we perceive as an edge might be a boundary condition in a larger structure. But even then, that boundary would not be an end of existence. It would be an interface. Let's consider observational consequences. If the universe had an edge within reachable distance, light traveling across it would behave differently. Waves encountering a boundary would diffract, reflect, or interfere. Over billions of years, this would imprint detectable signatures in large-scale structure patterns in galaxy distributions. Distortions in background radiation. Yet every deep survey we perform, from mapping galaxies to measuring cosmic microwave background fluctuations, reveals astonishing uniformity. The universe looks statistically the same in every direction. But what if the edge is unimaginably far away, beyond our cosmic horizon? Here we reach a profound limit. We cannot observe beyond the observable universe. Even if a boundary exists, if it lies farther than light has had time to reach us, it remains forever hidden. In that case, the universe could be finite with an edge and we would never know. Still, let's imagine it exists. Over cosmic timescales, the universe is expanding. Not just expanding, accelerating, driven by dark energy. Galaxies beyond a certain distance are receding from us faster than light due to expansion. In trillions of years, almost all galaxies outside our local group will slip beyond our horizon. The observable universe will shrink to a lonely island of stars. If there were an edge, cosmic expansion might carry it farther and farther away. In fact, space itself is stretching. The boundary would not be a fixed wall in static space. It would be moving outward as space-time expands. So could we ever reach it? Under current cosmological models, no. The expansion of space outpaces our ability to traverse it. Even traveling at light speed, we cannot overtake the accelerated expansion driven by dark energy. The edge, if it exists, would recede faster than we could approach. But let's shift perspective. Suppose the universe is finite and curved like the surface of a sphere, but in 3 dimensions. In that case, traveling far enough in one direction would eventually bring you back to your starting point. No edge, no wall, just global curvature. In 2 dimensions, the surface of Earth has no boundary, yet its area is finite. A 3-dimensional analog would mean our universe is the 3D surface of a 4-dimensional hypersphere. This geometry is mathematically consistent. Current measurements suggest that if curvature exists, it is extremely slight, so slight that the radius of curvature would be vastly larger than the observable universe. In such a cosmos, the idea of an edge dissolves. But what if there truly were a terminal boundary where space-time ends? Would time also end there? Space and time are intertwined. A boundary in space likely implies a boundary in time. Approaching it could resemble approaching the initial singularity of the Big Bang, where densities and curvatures grow extreme. Physics might transition into a quantum gravitational regime, where space-time becomes granular, fluctuating, uncertain. Quantum gravity theories like loop quantum gravity suggest space-time may be composed of discrete units at the Planck scale. If the universe had an edge, perhaps it would not be a smooth wall but a quantum foam. A region where the geometry ceases to have classical meaning. In that case, edge might not mean an abrupt stop. It might mean the limit of meaningful geometry. There's also a philosophical consequence. An edge implies asymmetry. One direction leads to termination. Others extend inward. That would introduce a preferred location in the cosmos. Yet one of the central principles of modern cosmology, the cosmological principle, states that on large scales, the universe has no preferred center or direction. Every observer, anywhere, sees roughly the same large-scale structure. An edge would violate that symmetry, unless the edge surrounds everything equally. Imagine living inside a vast cosmic sphere. Every direction eventually leads outward to the same enclosing boundary. In that scenario, there is no central privileged point. The boundary is everywhere at extreme distance. But again, we would expect subtle signals, reflections of light, repeated patterns in galaxy arrangements, echoes in background radiation. So far, we have found none, so where does this leave us? Current evidence suggests the universe is either infinite or so enormously large and gently curved that any edge lies beyond observational reach. There is no sign of a wall, no cliff in space-time, no detectable boundary conditions altering cosmic structure. Yet the question remains powerful because it exposes a deeper truth. Our intuition about edges comes from living inside larger systems. Rooms have walls because they exist within buildings. Planets have surfaces because they exist within space. But the universe is not inside something else, at least not in any confirmed scientific model. Asking about the edge of the universe may be like asking what is north of the North Pole. The question assumes a direction that loses meaning at the boundary. In the final analysis, if the universe had an edge, it would redefine our understanding of space, symmetry, and physical law. It would imply boundary conditions that shape everything inside. It would suggest a larger framework beyond our cosmos, or a fundamental limit where geometry itself dissolves. But the more we measure, the more the universe resists that idea. It appears self-consistent, homogeneous, and continuous beyond our horizon. And perhaps that is the most profound possibility. Maybe the universe does not end in a wall or a curtain. Maybe it does not curve back on itself in a simple geometric loop. Maybe it extends without boundary, or exists as a finite yet edgeless structure beyond our perception. If the universe had an edge, we would expect to see its fingerprints written across the sky. Instead, we see something else, a cosmos that looks the same in every direction. As though it has no preference, no boundary, no outside, which leaves us with a quieter, deeper realization. The universe may not have an edge at all, and the true boundary might not be in space, but in how far our understanding can reach.